So we started particle physics last week, and we discussed about the particles. So quickly, I will go through. First, we started with the concept of annihilation. When matter and antimatter join, they release energy. This is called annihilation, or we can also say when particle combine with its antiparticle, they annihilate or they release energy. And as a result, when annihilation occurs, it gives two photons to conserve the momentum as well. And what is a pair production? It's opposite of annihilation. When particle and antiparticle is produced by a photon or energy, we call that as pair production. The fundamental particles, some of the particles experience strong force, strong nuclear force, we call them as quarks, and some of the particle experience weak nuclear force, we call them as lepton. So this is a lepton family. You have 6 leptons, which are electron, electron neutrino, muon, muon neutrino, tau, and tau neutrino. Quarks, the particle which experience strong nuclear force, these particles are referred to quarks, and these quarks consist of up, down, strain, charm, top, and bottom. This is a charge, relative charge of these quarks, and the antiparticle, if it's up, anti-up will be represented by a bar. So these are the quarks you can see, and you can see their masses. So you will find the top quark is having the highest mass. You should learn the order. You should know which one is massive and which one is lighter quark. What are hadrons? Actually, particles which experience strong nuclear force, such as meson and baryon, are known as hadron. Baryon means it's a combination of 3 quarks. Meson means it's a combination of quark and antiquark. So proton is actually a baryon. Neutron is actually a baryon. Why? Because it consists of 3 quarks. And for every quark, the baryon number is plus 1 by 3. For antiquark, the baryon number is minus 1 by 3. So because the baryon, when we find the baryon number, because it consists of 3 quarks, so each quark is having plus 1 by 3. So when we add them, we'll get complete one whole number. So baryon number for each baryon is plus 1 and anti-baryon is minus 1. Mesons, what are mesons? The combination of quark and antiquark is called meson. And baryon number for meson is 0 because if one is quark and other is antiquark. So if one is plus 1 by 3, the other one is minus 1 by 3. So as a result, baryon number will be 0. So pi on, pi positive, kaon, these are examples of mesons. So basically the particles can be divided into leptons, which experience weak nuclear, hadrons, which experience strong nuclear. These hadrons are further divided into baryon and meson. Baryon means a combination of 3 quarks. Meson means it's a combination of quark and antiquark. Example of baryon such as proton and neutron, and examples of quark, examples of meson such as pion and kaon. And examples of lepton, electron, muon, tau, and their neutrinos and their antiparticles all are leptons. So example, a particle accelerator accelerates the proton through a potential of 1.8 giga electron volt. This is a voltage, 1.8 giga electron volt, which and makes them collide with antiproton. So basically proton and antiproton collided with each other. Same energy but in opposite direction. The collision create a proton and antiproton pair, like here you can see. So what happened means there's another proton and antiproton pair is there. So first you have a proton and there is antiproton, So one is proton, another one is antiproton, and they are moving towards each other, they collide, and this result in a formation of proton and antiproton pair. So we have to write the equation for this process as I mentioned. So as proton and antiprotons are there, they're creating this a pair of another proton and antiproton. What is the reason from how these particles are produced? So as you can see, when we apply the potential, so this proton was having a kinetic energy, and this one is also having its kinetic energy. So basically their kinetic energy converted into the mass, and when it convert into mass, the energy change into mass or matter, we call that as, when energy produce particle and antiparticle, we call that as a pair production. So there is a pair production, that's why you see proton and antiprotons. Now give one similarity between proton and antiproton. So what is the similarity between particle and antiparticle? They will have the same mass. And two differences between proton and antiproton, or two differences between particle and antiparticle. So they have opposite charges and they have opposite spins as well. Like example, if one is rotating clockwise, the other one rotating anti-clockwise. Or when you say a baryon number, because proton is a baryon, antiproton is also a baryon. So baryon, because proton consists of 3 quarks, where antiproton consists of 3 anti-quarks. So if baryon number for proton is +1, baryon number for antiproton will be -1. You can use that as a difference as well. Find the total kinetic energy of the proton and antiproton before they collide and give your answer in giga electron volt. So because each was moving with 1.8, so what will be the total? It will be 2 multiplied by 1.8, which is equals to 3.6 giga electron volt. The rest energy of a proton is 940 mega electron volt. State the rest energy of the anti. Rest energy or rest mass. Like example, if as a particle they move, there is a relativistic effect. What is a relativistic effect? Means the particle have a constant mass, but when they move close to speed of light, like example 0.8 times the speed of light, so what happens, their mass will not be constant, their mass increases. That's why we use the term rest mass. Rest mass means like when the mass is not changing or mass is constant, because when the particle moves closer to speed of light, their mass is not constant, they gain particles or Higgs bosons. That's why the mass will increase. And as the mass increase, so it will not be actual one what we calculated. So rest mass and rest energy means if it's an energy release if the particle have that specific rest mass. So if rest energy of a proton is 940 mega electron volt, it means this is the energy released by one proton. So same amount of energy will be released by antiproton, which is also equal to 940. Calculate the total kinetic energy of the particle after the collision. So how we can find the total kinetic energy of the particle after the collision? So you can see here, the kinetic energy, because what we need what will be the kinetic energy or what will be the speed at which these particles will move. So the total kinetic energy was 3.6, and energy to create the particle, how much energy is needed to create the particle? Because you need 940 mega electron volt to create the particle, one particle. That's so the total energy required to create one proton and one antiproton, that is equals to 940 multiplied by 2. That's why this is 940 multiplied by 2. This is a total energy required to create proton and antiproton. And this is the total energy available, the kinetic energy. So when we take a difference, the difference of like, but one is in giga, one is in mega. So you can convert this into giga and subtract. So you will find 1.72 giga electron volt. Is it clear? Because what happened, you have particle, antiparticle. As a result, when they combine with each other, they give another proton and antiproton. So these two masses will cancel out, balance. So basically, the kinetic energy is responsible for production of these particles. So it's not all of the kinetic energy used to produce the particle. Some of the kinetic energy used to produce the particle, and the remaining kinetic energy is a kinetic energy of the product. So what we did, we have the initial kinetic energy of the particles minus the energy required to produce the particles. So when we take a difference, we will know how much kinetic energy will be there for the particles which are produced. Is it clear, this example?
Yes.
Any doubt in this?
No.
Then for some interactions which involve a strange quark, we called a strangeness number. So the property strangeness is needed. Some reactions cannot happen, even though there are many things conserved, but the strangeness number should also be conserved. So the strange quark has a strangeness -1, and anti-strange is it's +1. And if all the other quarks are leptons, they all have strangeness 0. So if strangeness of a hadron can be found by adding the strangeness, how many particles are there? Example, so strangeness number, a property called a strangeness, it's need to explain why some reaction cannot happen. Like example, for some reactions, when we find the charge, it is balanced. When we find, or it is say equal, when we find the mass, that's also conserved, momentum is conserved, but still the reaction does not proceed. So if the reaction does not proceed, to explain the idea why the reaction does not proceed, we use the strangeness number to explain. So strangeness number, it's for every strange quark, it is -1, and for anti-strange, it is +1. Copy this strangeness number. So example, beta decay can be negative beta decay. It can be positive beta decay. What's the difference? Negative beta decay means electron is released, and positive beta decay means positron is released. Not proton, positron. Positron is antiparticle of electron. So example, if there's an equation, in a beta decay, a neutron decay to produce a proton, electron, and anti-electron neutrino according to equation. So you can see this equation. So if neutron break into proton, electron, and anti-electron neutrino. So we can also write this equation in terms of quarks. What is neutron? Neutron is actually up, down, down. And what is proton? Proton is up, up, and down in terms of quark composition. You should remember these compositions. For a neutron, it's up, down, down. For proton, it is up, up, and down. That's why for a neutron, neutron is a neutral particle. Why it's a neutral baryon? Because it is up, down, down. So up is +2/3, down is -1/3, and -1/3. So when you solve, you all cancel out. So that's why you're left with 0. So neutron is a neutral particle. Whereas proton, it is up, up and down. It's also a baryon because it's a combination of three quarks. So up is 1 by 3, up is plus 2 by 3, and that's also plus 2 by 3, and then minus 1 by 3. So when you solve, you will get a charge as relative charge is plus 1. That's why this is charge is positive. So it is up, up and down. Electron is a lepton, so you cannot write in terms of quark. And anti-electron neutrino is also a lepton, so you cannot write in terms of quark. So if we cancel out the common, like how we cancel out, you can see this can cancel with this, it's the same. Up can cancel with up. So what we are left with, it can be, so basically what happened in this reaction, there's a down quark which gives an up quark electron and electron neutrino. Is it clear?
Yes.
And same way, if you check a positive beta decay means a positron is released. So a proton decay to produce a positron and electron. So proton gives neutron, positron and electron neutrino. So when we write in terms of quark composition, it is up, up and down. This is up, down, down. And when we simplify this, so what happened? Like up will cancel with up, down will cancel with down. So it means up quark change into down, positron and electron neutrino. So the equation we can just work out. You can see it started with concept of neutron, that neutron, it happened with neutron, but in reality it's not happened with neutron. It's a down quark which changes and give a result. Same thing, it in a positive beta decay or a positron emission, a proton is first changed to neutron and positron and electron neutrino, but in reality when we simplify, it is a up quark which gives down quark, positron and electron neutrino. Then when there is a particle interaction, and what we have to check in interaction, the following are conserved: energy, momentum, charge, spin, lepton number, baryon number. And in any interaction involve a strong force, like example a strange quark, so the strangeness should also be conserved. So example, we'll do some examples here. So we should always check how to check a conservation of a baryon number. As we know, for baryon, because baryon consists of 3 quarks, so each quark having a baryon number 1 by 3. So that's why 1 by 3 plus 1 by 3 plus 1 by 3. So total baryon number for each baryon is plus 1. For meson, because it's a combination of a quark plus anti-quark, so that's why it is 0. And anti-baryon, all anti-quarks are there, so that will be minus 1. And when we check lepton number, you can see the lepton number for each lepton particle is plus 1, and for all the anti-particles it is minus 1. Now we'll discuss some interactions. So example, the first figure shows a beta decay, a negative beta decay. First we check the charge, because what we have to check the charge should be conserved, lepton number should be conserved, baryon number should be conserved, spin should be conserved, and strangeness also should be conserved. So neutron give proton, electron and anti-electron neutrino. So when you check the charge, neutron is a neutral particle, so charge is 0. When you check the charge, the total charge of a proton, it's a positive plus 1. Here it's a relative charge because actual charge of a proton is 1.6 exponent minus 19. But when you compare in terms of 1.6 exponent minus 19, so they have the same ratio for electron and proton. That's why it's called plus one. Electron minus one, and anti-electron neutrino, all electron neutrinos or anti-electron neutrino, their charge is zero. So you can see here, this side is zero, plus one and minus one, so that also makes zero. So it shows that the charge is conserved both sides. So tick for the charge. Then you check the lepton number. Lepton number, for every lepton it is plus one, and for anti-lepton it is minus one. Neutron is a baryon, so it's not a lepton, that's why it is zero. Proton is also a baryon, it's not a lepton, so it is also zero. Electron is a lepton, so that's why it's plus one. An anti-electron neutrino, it's an anti-particle, so lepton number will be minus one. So when you check the lepton number on the right hand side, it's zero. On the left hand side, it is also zero. So what it shows that the lepton number is conserved. Then you check the baryon number. Baryon number, for every baryon it's plus one, anti-baryon is minus one. Neutron and proton are baryon, so the baryon number is 1, 1. And these are leptons. For lepton, the baryon number is 0. So on the left hand side, baryon number is 1. On the right hand side, baryon number is 1. So that is also conserved. Spin, half spin. In the beginning, I explained the spin of each particle. Neutron having a half spin, proton having a half spin, electron having a half spin, but anti-electron neutrino having opposite half spin. So these two will cancel out. So you can see the spin is also conserved. Then the strangeness refers to if there is any strange quark, that's called a strangeness number. So what is neutron? Neutron consists of up, down, down, and this is up, up, and down. So there is no strange quark, that's why it is zero. There's no strange quark, zero. Lepton strangeness number 0, and anti-electron neutrino strangeness number is 0. So it shows that all are conserved. So if for a reaction all are conserved, it means this reaction or interaction does not violate any conservation law, so it can occur. Is it clear?
Yes.
Same way, when you check another reaction, so in this reaction, use the conservation law to show the so there is a kaon positive interacted with anti-proton, gives kaon negative and proton. First we check the charge. Kaon charge is plus one, proton anti-proton is minus one, k negative minus one, so charge is conserved. Lepton number, kaon is a meson, so it's not a lepton, so for it's 0. Proton is a baryon, so for baryon also lepton number is 0. K minus is also a meson, so lepton number 0. Proton is also a baryon, so lepton number 0. So lepton number conserved. When we check baryon number, for every meson it is 0. For baryon it's plus 1, and anti-baryon is minus 1. So when you check for kaon, the baryon number is 0. Proton, anti-proton, it's because it's an anti-particle, baryon number minus 1. But for proton, baryon number plus 1. So you can see the baryon number on the left hand side and right hand side is not equal. So a baryon number is not conserved. So this interaction cannot occur or cannot happen. Is it clear? So if we we check the charge, lepton, baryon, if baryon number is not conserved, we'll not move on to the next part. We'll stop at that one. About the spin 1, because spin should be conserved, but the thing is Normally, you don't have to check the spin. You normally check lepton, baryon, and strangeness number. So another question: if the rest mass of electron is 9.1 exponent minus 31, find the energy in joules, and this could be theoretically converted into a photon. So how to find energy? We have the formula E is equals to mc square. E is the energy which is produced, m is a mass, so mass is equals to 9.11 or 9.019 exponent minus 31 kilogram multiplied by speed of a light square. So speed of a light is 3 exponent 8 and then square. When you multiply, you will get this energy in joules. In the next one, as we have said that the reaction occur in particle accelerator, that proton and proton. Example, give two protons, one more proton and antiproton. If the rest mass of a proton or antiproton is 1.6 exponent minus 27, calculate the minimum total kinetic energy for the incident particles. So how we can find the minimum kinetic energy for incident particle? Because what happened if two protons are producing two protons and one proton and antiproton? So these two particles produces proton and proton. What about these two? So these proton and antiproton, to produce this proton and antiproton, what we need energy, and that energy from where it will come? It will come from kinetic energy. So we will use the formula E is equals to mc square. So m, what a m I will substitute? That m will be the mass of proton and the mass of antiproton, and multiplied by speed of a light square, I will get how much energy is needed for the incident particle. Is it clear? The second one.
Yeah.
Which of these reaction is forbidden by conservation of the charge? Means because of the charge, this reaction will not occur. So when you check the first one, proton, proton gives proton, proton, then pi positive and pi negative. So you can see here, these two will cancel out. So charge plus 2, charge plus 2, so this can occur. But what about this one? So this cannot cancel out. So there is extra positive charge on the right. So this reaction is forbidden in terms of conservation of charge. Is it clear?
Yes.
Because you have to remember the charges here as we discussed the mesons. So you can see here the charge of pi positive is +1 and qion is also +1, K positive. And its NT is pi negative and qion negative. Same way, which of these reaction violates the conservation of lepton number? So you have to check a lepton. This is muon, anti-muon basically. Gives antiproton plus anti-electron neutrino plus anti-muon neutrino. So for every lepton, the lepton number, because we just have to check the lepton number, not all. In this we have to just check lepton number. So for every lepton, it is +1, and for anti-lepton, it is -1. So when we check, because it's anti here, anti-mu particle is there, so this is anti-particle, so lepton number will be -1. This is anti-particle of electron, lepton number -1. This is anti-particle, so -1. And this one is lepton, so +1. So when you check, is it conserved? So you can see that this is not violating. It's conserved because these two will cancel out. So you're left with -1 and -1. Both sides is equal. So it can happen. Other one, you have muon, anti-muon neutrino plus proton gives muon and neutron. So for every this is a lepton, so lepton, anti-lepton, it's -1. This proton is a baryon. Baryon number is, for every baryon, lepton number is 0. And muon, it's also a lepton, so it will be +1. And for neutron, it's a neutron is a baryon, so lepton number 0. So this interaction cannot occur because it violates the lepton number. And when you check for this one is -1, -1, and this is gamma. And you can see here the gamma particle. It's not a lepton. It is refers to energy, like a photon. So that's why the lepton number will be 0, so that this interaction can also occur. So all these show that these interaction conserve the charge and the baryon. So when you check the charge, proton, so 4 proton and a pi neutral is there. So 4 proton, and so the charge of a proton +1, +1, +1, +1, and because the pi neutral, so that's why there is no charge, so charge is conserved. When you check the baryon number, for every baryon it's +1, anti-baryon is -1, and meson it is 0. So baryon number is also conserved. When you check for the second interaction, when you check the charge +1, +1, this is conserved, and baryon number is also conserved. Is it clear, these interactions?
Yeah.
Now, sometime you have to identify the unknown particle. So example, a muon can decay as follows. A muon is there, it gives a electron, and it gives the electron, sorry, muon neutrino, and another particle X. So how we can find this particle X? So as you can see, you have to check the conservation. So like what should be the particle X? So first we have muon. It is decaying into electron, muon neutrino, and another particle X is released. We don't know what is X. So first when we check the charge here, the charge, because muon, electron, and tau, all they are leptons, they have a charge -1. So this is charge -1. Electron charge is also -1. Electron neutrino, muon neutrino, and tau neutrino, their charge is 0. So because the charge is conserved, so this element X this particle X should have 0 charge. So charge of the X should be 0. That's we identify. Then we check the baryon number. Muon is a lepton, so baryon number is 0. Electron is a lepton, so baryon number 0. Muon is a lepton, baryon number 0. So because the baryon number left and right hand side is 0, so what should be the baryon number of this? The baryon number of this particle should also be 0. Then you check the lepton number. So when you check